Okay, great. I hope you can hear me. I think the microphone is working. Okay, hello everyone, and welcome to my talk. My name is Ana Maria, and I'm a mathematics master student at ETH. And today I will be telling you about Markov's theorem on Diophantine approximation and the uniqueness conjecture. So let's start first with Diophantine approximation. Maybe some of you are familiar with the field or not. Like, how many of you have done anything in with Diophantine approximation? Can you raise your hand? Very few of you. Okay, okay, cool. That's why we're here. We want to introduce that field. So Diophantine approximation is concerned with how well can real numbers be approximated by rational numbers. And that's quite an old question in number theory. The fact that it's called Diophantine approximation already tells you it started with this guy Diophantine, which was a Greek guy, so it started quite a long time ago. But it's still a very much alive field, and there's plenty of research going on in it. So how well can a real number be approximated by a rational one? And for example, let's say I ask you to approximate pi. Maybe somebody would say it's 3.14 or 3, which is quite sad. Maybe a bit better approximation would be if you would say it's 355 over 113, which sounds a bit random at first, but I will explain to you how I got this number. But this is still not good enough. I mean, we get a bit more digits, but it's not good enough. Or you can just answer this question very easily by saying, okay, I know plenty of digits of pi, so I can take all these digits I know and make a fraction by simply dividing by 10,000, and get arbitrary close to pi as I want. Or I can write out the continued fraction expansion of pi, and that's exactly actually how I got this fraction up there. I took just the first few terms of the continued fraction expansion, and I just summed them up. But okay, in the end, how well can a real number be approximated by rationals? The answer is arbitrary well. We can find sequences of rational numbers which approximate the real number as nicely as we want. But the problem with such a sequence that we find is that these denominators, qn's, like we have here pn over qn, they often grow very rapidly. And we want to have a bound on how well this real number can be approximated, but such that we can also control how large the denominator grows. And what we do is we complicate the question. We ask, how well can a real number be approximated by rational numbers such that the denominator only varies slightly? And in this context, very slightly means that the absolute value of this distance between the real number and the rational number can be well bounded by a bound depending on q. Okay, and that's a fair question. And Dirichlet, there's a classical theorem by Dirichlet which gives the first attempt to answer this question. And he said that if we take a real number and an arbitrary positive integer, then there exists a rational number p over q such that the denominator is smaller or equal than n, and such that we have the following inequality. So we can bound this distance from the right-hand side by 1 over q n. And this also tells us that since q is smaller or equal than n, this means that this distance on the left side is smaller than 1 over q squared. So we have a bound depending on q to the power of -2, which is pretty nice. So, okay, great. We have a bound from above. So what about bounding from below? And there is a theorem by Leville, and he says that if we take an irrational number, which is algebraic with degree d, then there is a positive constant such that we can bound from below by c over q to the power of d for all rational fractions. And if we introduce a bit of terminology, we can say that a real number is approximable to order d if there exists a constant which depends on that real number and infinitely many fractions such that we can bound this difference also from above by the constant divided by q to the power of d. And then one can show that a corollary of Liouville's theorem is that an algebraic number of degree d can be approximated to order at most d. Okay. And I will not go into the proofs of these theorems. They're actually rather simple, but what I rather want to talk about how these theorems can be applied. And I mean, if you look at them for the first time, they look quite boring, to be honest. But they can actually be quite useful, and they can be useful in a sense that we can, with the help of these theorems, we can figure out whether some numbers are transcendental. And I mean, whether a number is transcendental is quite a big question in mathematics. Like, we know maybe like pi is transcendental, e is transcendental, but what about pi plus e? We don't know. Pi to the power of pi, we also don't know. But something that we do know is that, something that we can show is that this number alpha that I have written up here, this infinite sum from n equal 1 to infinity of 1 over 10 to the power of n faculty is transcendental. And how do we do that? Like, we can, as I said, we can use this corollary by Liouville, which says that an algebraic number of degree d can be approximated to order at most d. So if we have a real number which can be approximated to any order, then it must be transcendental, right? So all we need to show is that if we pick a real number, we can choose infinitely many fractions such that we can approximate that real number, then that it can be bounded from above by some constant depending on the real number divided by q to the power of any positive integer. And I will show that. So the claim is that this number is transcendental, and we can do this relatively easily. So we pick an arbitrary integer, which is a big N, and for all integers greater than that, we define these partial sums, which are just the sums from L equal 1 to N of 1 over 10 to the power of L faculty. And then we look just at the difference of alpha minus p over q, and we want to bound it nicely. And we can write that out, factor out 1 over 10 to the power of n plus 1 faculty, and we can use this really bad approximation that this term is smaller than this term 1 over 10. Like these terms in the brackets, that they're smaller than 1/2, 1/4, 1/8, and so on. And if we sum up the telescope sum in the end, what we end up with is that this is smaller than 2 over 10 to the power of n plus 1 faculty, and that tells us that this difference of alpha minus p over q is smaller than 2 over q to the power of n. And that's exactly what we wanted, because n was arbitrary, chosen at the start. And what we found is infinitely many of these fractions, which we can like define really easily by those partial sums, such that this difference is nicely bounded. And that was exactly what it means to be approximable to order n. And since it's approximable to every order n, alpha is transcendental. And this was actually how Liouville constructed the first, I think, transcendental number back in the day when he was alive. And I mean, we can replace this 10 with also some other integers, and the proof will work very similarly. But it's nice to have concrete methods to figure out whether a number is transcendental. That's quite a hard question. But okay, let's return to the Diophantine approximation. So we have seen this theorem by Liouville, which gives us a bound from above, which has degree d. And we can ask, okay, can we maybe sharpen Liouville's theorem to an order of approximation smaller than d? And it turns out that we can. And Roth gave an answer to that question. He also received the Fields Medal, I think, in 1958 for his work. And he said, if we take a real number and a positive epsilon, then there exist infinitely many fractions, with this difference of alpha minus p over q bounded from above by 1 over q to the power of 2 plus epsilon. Then we have that the real number alpha is transcendental. Okay. So what does this theorem tell us? It tells us that we cannot do better than the bound 2 on the right-hand side. Like, we cannot improve we cannot improve the exponent 2 on the right-hand side on the bound. But what we could do is we could improve this constant 1 that we have on the right side. And Hurwitz made the first step into that direction, how one can prove that. And he said, if we take an irrational number, and this funny constant square root of 5, k equal to square root of 5, then there exist infinitely many rational numbers, p over q, such that we have this inequality, where now on the right-hand side we have 1 over k times q squared. Okay, so there's a constant has appeared, But something funny happens if k is greater than square root of 5, because if it's greater than square root of 5, then there exist infinitely many irrational numbers which are dense everywhere on the real line. And for each one of them, if you choose each one of them, it will satisfy this inequality up here only for a finite number of rational fractions. Okay, and this seems a bit weird. I mean, why did we choose square root of 5, and what kind of irrational numbers can we choose which are dense everywhere? And I can also tell you which ones can we choose, and you can see from the proof which ones are those. And for the moment, I want you to just stick with it and believe me, and you will see later like that actually comes from another bigger construction. But for now, something that you can choose, just to give you an example, is you can choose for alpha to be the golden ratio. And not only that, you can let the group SL2Z act on the golden ratio, and any number that we get will be in this second category, like in this second part of the theorem for any k greater than square root of 5. So if you choose the golden ratio and look and choose some k greater than square root of 5, we can find only finitely many fractions which will satisfy this inequality given in equation 1. Okay, and like the proof of Hurwitz theorem was initially given using some continued fractions, and that is pretty nice. But what I want you to do now is to think of this problem geometrically, and I think it's pretty nice how one can like look at this problem, which at first doesn't seem to be geometric, but then now it makes sense why I talked about the distance on the left-hand side the whole time. And how we can think of it geometrically is, okay, we consider the upper half plane, and this rational point alpha is somewhere placed on the real line. And what we do is, through the point alpha, we're going to draw a perpendicular line which passes through it, which now here I call L. So we just draw a straight line, and then we consider rational points P over Q, and at each rational point we're going to draw a circle which is tangent to the x-axis at one point, namely P over Q, and has radius 1 over k times Q squared. And now the idea of this construction is that if we have that the circle S, which I called S in this case, it's blue, intersects the line L, then we have the distance between alpha and P over Q is smaller than 1 over k times Q squared. Okay? So that's how you can think of the problem geometrically, and you can prove the entire statement also geometrically. How you do that is, I'll just give you a short idea. So we consider now not only the point P over Q and alpha, but we also consider this circle and the line L, and we let this group SL2Z, which is like 2 by 2 matrices, determinant 1, and integer entries, act on the points on the upper half plane by modular transformations, which is precisely this action AZ plus B divided by CZ plus D. And what we can do is we don't have to look at the entire upper half plane, but it's sufficient to just look at parts of it. And if you let this modular transformation act on this construction, what we can do is we can send the point P over Q to infinity. And what then happens is this line L gets sort of flipped over into a half circle, which is denoted by L dash. And then the idea is that we, at the end, don't have to look at all circles in the upper half plane and all possible lines L that can appear, but we can limit ourselves to just looking at the small region on the upper half plane. And some of you, maybe if you know some hyperbolic geometry, you know that it's enough to look at the fundamental domain, because the fundamental domain is this region that I denoted by D in the upper half plane, and it has this unique property that if we pick any point in the upper half plane, there exists a unique matrix which is like almost unique matrix which maps that point into the fundamental domain. So we don't have to consider everything, and we can just limit ourselves to looking at lines L which intersect this region. And then what we care about is when does this line L and with what properties intersect these circles that appear from letting the group SL2Z act on the circle that we started with. Okay, so that's just the rough idea. I mean, there's a lot of details to be worked out here, and I'll give you some references if you want to look at it. But yeah, I think it's pretty nice that we can imagine this theorem completely geometrically. Okay, so now I want to turn to a seemingly unrelated problem, which is this funny equation called Markov's equation. So a Markov triple is a triple of positive integers which satisfies this equation, a squared plus b squared plus c squared equal to 3abc. And we say that the Markov number is a number which appears in some Markov triple. So the fact that they have so many Markovs and they all have names already tells you it's quite important. Like, okay, we can look at some solutions of this equation. Like the simplest solution is obviously 1, 1, 1. We have also 1, 1, 2, 1, 2, 5, 1, 5, 13. And I write these solutions such that C is always the greatest, the biggest number in the triple. And we can also have a formula for new solutions. If we already know that ABC is a Markov triple, we can take A dash BC to be 3BC minus A, B, and C. And completely symmetrically, we can say that A, B dash C is like A, and so like we can completely symmetrically write out this formula where we put the first part in place of B. And also these solutions form also a graph. You have seen it at the first slide. I mean, it's not really relevant, but the graph looks nice. And what we can do is, if we look at these solutions, is we can form a sequence of Markov numbers which satisfy this equation. And the sequence starts with 1, 2, 5, 13, 29. I think the next number is 43, and so on. And okay, this equation looks quite simple, but it turns out there's a lot of stuff we don't know about it. And one of those things is, if you look at these few solutions I wrote out here, you see that each one of these Markov numbers, and we say that the Markov number is just a solution of this equation, appears as a maximum in each one of these triples. And we can ask ourselves, okay, does every Markov number appear as a maximum? That's a fairly interesting question, and the answer is yes, it does. Okay, and we can also show that. But okay, if it appears at least once as a maximum in the Markov triple, does it happen again? So are there maybe two different Markov triples which have the same maximum, but the other two integers are different? And it turns out that we don't know. And that is precisely the uniqueness conjecture, that every Markov number appears exactly once as the maximum in a Markov triple. Like, we don't know. There has been made some progress, I think, using some algebraic number theory, and many cases have been proved, but finally the whole conjecture has not been solved entirely to this day, I think. So all in all, we don't know so much about this funny equation. So what does this equation have to do with approximating real numbers? That's what I want to tell you about now. So let's get back to Diophantine approximation. So I want you to recall the theorem by Hurwitz that we have talked about before, and I told you if we choose a real number to be the golden ratio, which is 1 plus square root of 5 divided by 2, and if k is greater than square root of 5, and we consider this equation like this inequality given in equation 2, then there is only finitely many fractions p over q satisfying it. Okay, but Hurwitz went also a step further, and he stated the following. He stated that if alpha is now not equivalent to the golden ratio, and when I say not equivalent, I mean, I'm not sure if I had defined this, but I say that two irrational numbers are equivalent if there is a modular transformation which maps one to the other, i.e. there is a matrix in SL2Z with that action that we have seen some time before. Here is that action, which maps one to the other. And we say that two irrational numbers are equivalent if one can be mapped to the other by an action in SL2Z. Okay, great. So we have been here. So if we, and Hurwitz also stated that if we take an irrational number, which is not equivalent to the golden ratio, then there exist infinitely many fractions satisfying this inequality if we now choose k equal to square root of 8. But if k is greater than square root of 8, then there are only finitely many fractions satisfying this equation. Okay, and Hurwitz stopped here. He did not go further. But something that we see from this statement is that we have a very completely analogous statement as with square root of 5. Just now we have the square root of 8 and this extra condition that it's not equivalent to the golden ratio. And this hints at there potentially existing some sort of sequence which starts with square root of 5, then square root of 8, and then comes something else. Which sounds funny. I mean, what does Markov's equation have to do anything with approximating real numbers? To explain what happens is I need to introduce just a bit more terminology. We say that a real number is badly approximable if there exists a positive constant such that this difference, alpha minus p over q, in absolute value is bounded from below by the constant divided by q squared. And such that this holds for every rational number in Q, which is different from alpha. So, okay, that means badly approximable. And we again consider the problem we had been thinking about before. Namely, if we take an irrational number, we're looking for all positive real numbers, such that the absolute value of alpha minus p over q is bounded from above by 1 over L times q squared for infinitely many fractions. And I introduce one more definition. And if we take a real number, we say that the Lagrange numbers, L of the real, denoted by L of the real number, are given by the supremum of L taken over all real numbers L satisfying this condition above. And a collection of these Lagrange numbers just forms the Lagrange spectrum. And this definition is a bit technical and a bit hard to imagine, but we'll talk about it a bit more. Now, because Markov's theorem, which is one of the main topics of this talk, is precisely a result about the Lagrange spectrum below 3. And okay, now we can finally come to Markov's theorem. So it looks quite long, but the nice thing about Markov's theorem is that it's very explicit. So even though it's quite a long theorem, we know explicitly what we're working with. And the theorem goes as follows. So let A, B, C be a Markov triple, and let P1 and P2 be positive integers which satisfy this weird condition. And as a setup, we define these two numbers x and k, where x is some weird stuff which depends on A, B, C, P2, and k is equal to the square root of 9c squared minus 4 divided by c squared. And okay, now that we have this setup, Markov says the following. He says that then there are infinitely many fractions satisfying this inequality we were looking at the whole time. So x minus p over q smaller than 1 over k times q squared for this x given up there in the setup. But there are only finitely many for any larger value of k. And in other words, this says that the Lagrange spectrum of x is given by k explicitly. And conversely, suppose that we take an irrational number such that only finitely many fractions satisfy this inequality up here. For some k smaller than 3, then there exists a unique sorted Markov triple such that this irrational number is equivalent to x by given in this equation 4. Okay, so how does one work with this theorem? I mean, it's quite long, and what did it actually say? The easiest way to maybe think about it is to start with some examples. So we know a few solutions of Markov's equation. The easiest one is 1, 1, 1. So we can try to plug it into this formula and see what happens. So if you choose A, B, C to be 1, 1, 1, and you can also see this for yourself, and we can choose some integers which satisfy this thing, and we can then compute that that k is equal to square root of 9 minus 4 divided by 1, or square root of 5. And if k is equal to square root of 5, we can get that x is equal to precisely the golden ratio, 1 plus square root of 5 divided by 2. And then Markov theorem just says the same thing that Hurwitz theorem said. It says that there are infinitely many fractions satisfying this inequality, but only finitely many for any larger value of k. So in the case of taking the first Markov triple, we get precisely Hurwitz theorem. So what happens with the second Markov triple? We can do the same thing. ABC is equal to 1, 1, 2. That was the second easiest solution. And then if we compute k, so we insert c equal to 2, we get that k is equal to 9. And x is equal, I think, to 1 plus square root of 2, but I mean, that's a bit less relevant. And what Markov's theorem says is that then there are infinitely many fractions satisfying this equation, where k is equal to square root of 8, but only finitely many for any larger value of k, which is exactly the next statement that Hurwitz gave. So about square root of 8. So Markov's theorem gives us this whole sequence, sort of theorems, which give us a correspondence, which is a one-to-one correspondence between solutions of that funny equation, that Markov equation that we saw before, and between equivalence classes, right? Because in this corollary we look at x dash, which is equivalent to x, and between equivalence classes of actually badly approximable irrational numbers. And said a bit more nicely, in other words, the Lagrange spectrum below 3 is given by this set of irrational numbers given by the square root of 9 m squared minus 4 divided by m, where m are these Markov numbers. And yeah, I have already told you that from the first few Markov numbers we can compute these Lagrange numbers, square root of 5, square root of 8, and the next one would be square root of 221 over 5, and we could make a very similar statement to Hurwitz theorem. Okay, so, I mean, this is pretty neat to tell us that there is this explicit correspondence which we can also compute really nicely. But Markov's theorem does not stop there. Something else that Markov was wondering about is quadratic forms, and he was asking himself how well can quadratic forms be bounded from below. So what is the smallest non-negative value a quadratic form can attain? And for that, let's first just introduce what are binary quadratic forms. So binary quadratic forms are are given by this expression: f of pq is equal to ap squared plus 2b pq plus cq squared, where a, b, c are real numbers. And we say that they're indefinite if they have positive discriminant. And we do that because in this case, if they're indefinite, we get two distinct roots for the polynomial f of p1. So it's just a technical condition, you can almost forget about it. And so okay, great, we get two roots. If a is not equal to 0, right? If a is equal to 0, that's nonsense. But for a equal to 0, just for technical reasons, we define like minus c over 2b and infinity to be two roots in the real projective line. Okay, and what we're now interested in is to look at how well these forms can be bounded from below. Like what is the lowest number they can attain if they're not equal to 0? And for that, we first want to know, okay, when are they equal to 0? To exclude those cases. And we have the following statement. We have that f of p of 1 has at least one root in q together with infinity if and only if there exist integers p and q which are not both 0 at the same time, such that f of pq is equal to 0. Okay, so now that we have determined when binary quadratic form is equal to 0, we turn to that problem of trying to bound them from below efficiently. So we're looking for indefinite forms for which this set f of pq, where p and q are integers, not both 0 at the same time, stays farthest away from 0. To make this explicit without words, we define this constant m of f to be the infimum just of this absolute value of f of pq, where pq is in z squared. And this technical condition of dividing by the square root of the discriminant, it doesn't have to be there. It's just here to normalize the thing a bit, because these values of these forms can get quite large very fast, and it's neat if we can normalize it nicely. Okay, so we're looking for when is m of f maximal. So, and why is this useful? This is useful because if we have that f of pq is not 0, then we can bound the quadratic form from below by this constant m of f times the square root of the discriminant. And there's a theorem by Korkin and Zolotarev which says that if you take an indefinite binary quadratic form with real coefficients, which is for some reason equivalent to this form, and I will explain to you in a moment what it means to be equivalent, which will actually be completely, this equivalent is completely analogous to the equivalence we had for irrational numbers. But okay, if we have a form which is equivalent to this, then this constant m of f is given by 2 over square root of 5. Okay, so square root of 5 is appearing again. So that's already spoilers. And otherwise, this constant m of f is smaller than 1 over square root of 2. To just tell you what it means to be equivalent means that there exists a matrix again in SL2Z, such that we have this relation like f, like two forms, f and f tilde, and f tilde of pq is equal to f of ap plus b q and comma cp plus dq. Okay, and you'll see in a moment why I gave you this theorem. So now that we have this, we can state Markov's theorem in the quadratic forms version case. And it goes as follows. It looks actually completely analogous to the Markov theorem that we have seen before, just that now certain things are sort of translated into the language of quadratic forms. So if ABC is a Markov triple, and we have two integers satisfying, again, this weird condition, and the very completely identical setup with x0 to be equal to this, and k be equal to this square root of 9c squared minus 4 divided by c squared. And if we let f to be this quadratic form, indefinite quadratic form, which depends on x0 and k, it looks like p squared minus 2x0 pq plus some stuff depending on x, q, and k. And if we have all of this, then m of f is equal to 2 over k. So this infimum that we had, that I had defined here, is attained. And that's pretty nice, because, I mean, we can just compute this constant m of f and plug it in here, and we know what are the lowest values that f of p, absolute value of f of pq can take. So that's pretty neat. And it gives also a converse. Conversely, suppose that f tilde is, we take an indefinite binary quadratic form such that m of f tilde is greater than 2/3. Then there is a unique sorted Markov triple such that f tilde is equivalent to a multiple of a form given in this equation. And equivalent is, by equivalent I mean that there is a matrix such that the things above hold. So Markov's theorem, if you look at both the quadratic forms version and the Diophantine approximation version, it says that there's an equivalence between, there's a direct correspondence between Markov triples and between, on one side, between equivalence classes of badly approximable irrationals, and between equivalence classes of indefinite binary quadratic forms with certain properties of how well can they be bounded from below. And I mean, that's quite surprising. something more that is surprising about this theorem is that it also can be proven entirely geometrically, like in the proof of Hurwitz theorem. Maybe I'll talk about that a bit at the end, but for now I want to talk a bit about the Lagrange spectrum above 3. So Markov's theorem has told us about the Lagrange spectrum below 3, and what we have seen is that we get these discrete points, square root of 5, square root of 8, square root of 221 divided by 5, and blah, 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 so on. And the Lagrange spectrum, it converges to 3. We can see that by looking at this value of k, which is square root of 9c squared minus 4 divided by c squared. So we can let c tend to infinity, and we just get that 3 is a limit point. So below 3, it's completely determined. We know what exactly happens, and it's pretty nice. We know what happens using Markov's equation. So what happens above 3? Well, the situation changes a lot. There's many gaps, weird stuff is happening, there's uncountably many limit points, and so on. So it's not so nice. But something that Feynman discovered is he said that the Lagrange spectrum contains every number above the Feynman number, which is this weird fraction which is between 4 and 5. So below 3 is discrete. Between 3 and this weird number, some weird stuff happens, and above it, it's just a continuous line. So, yeah, that's about the Lagrange spectrum. Above 3. So about the geometric proof of Markov's theorem. The idea is very similar to Hurwitz theorem. Maybe I just give you a bit of the idea, and if you want, you can check it out more later. And the idea is to we again look at circles in the upper half plane, and we define certain hyperbolic distances between these circles, in between circles and half circles, which are actually geodesics in the upper half plane. And what we can do again is we don't have to look at the entire plane, but we can limit ourselves to looking just at a certain region of the upper half plane, which again tessellates the whole plane. And this region that we can look at is actually a squarey thing, which has a point at infinity, and I mean it's a hyperbolic rectangle. It's a hyperbolic rectangle, and what turns out is to happen is we have an equation for the distances between these circles, which is called Ptolemy's equation. Like here, I denoted these distances by A, B, C, D, and F, and these distances satisfy an equation which looks like AC plus BD is equal to EF. And if we use that equation nicely, we can sort of sum up certain lengths of arc lengths of circles to end up with a problem of looking at when a certain circle has this property that it's equal to 2 times A over BC plus B over AC plus C over AB. And how we obtain this circle is you look at this weird hyperbolic rectangle and you glue it together, and you get, if you connect all these arc lengths of circles, you get a big circle. And it's quite complicated, and I know it doesn't maybe make sense now if I tell about it. But if you want to look at the details, if it interests you how to work this out, you can maybe check it out. But eventually what you end up with is an equation like this. And if we limit ourselves to looking at circles on a torus, which have length 6, then we have that this is precisely Markov's equation. Okay, so that's fairly complicated, but here's some references. You can, if you want to check it out, you can check out this paper by Boris Springborn, which gives you the geometric proof of Markov's theorem, or you can check this. If you want to look at Hurwitz theorem geometrically, there's also this. This paper by Ford. And Eigner has also a nice book on the topic and on the uniqueness conjecture and how far we went until 2013. So, yeah, thank you very much. Are there any questions? Yes?
I was wondering, is there an intuitive or geometric explanation for the role that the golden ratio plays in this approximation?
Yes. wait, let me get to the picture. How do we get the golden ratio? So if you try to prove Hurwitz theorem, like I told you already about, so we look at these rational points and we construct these circles in the upper half plane. And then we let the group SL2Z act on them so that we get a whole bunch of circles in the upper half plane. But apart from these circles, you also see this horizontal line, which I called here y equal to k over 2. And this horizontal line also comes from a circle, and you can sort of imagine it as a circle at infinity. Okay? So sort of that's how you imagine it. And now the idea of the proof is, the thing is, if we change k, we change the radius of this circle. And not only one circle, but all of these circles. So they can all get smaller, and this k up here, this line, gets further up if they get smaller. That's sort of how you can imagine it. And now the problem is to choose k such that these distances between all these circles and this horizontal line y equal to k over 2 gets so close together that the only half circle, which is here in red, we can draw is this C, this weird circle here, such that it does not intersect any circles. Like that's the goal. And the thing is, after we end up with this half circle C, and if we look at the endpoints of it, we will get 1 plus minus square root of 5 over 2. So that's where the golden ratio appears. So and how we get these endpoints is like, maybe you see these thin red lines, but we get this triangle that we know stuff about, and we use the Pythagorean theorem. Yeah. Did this help you? Yeah. Okay, great. Is there more questions? No more questions? Okay, if you think of a question, you can also ask me at the upper row. So, yeah, thank you again.